All right, so today we're going to talk about the basics of signal filtering. So we'll look at the overview in this lecture, and then the further lectures will have examples of how to do different kinds of filter designs. So filters are used mostly for getting rid of noise. A noise in a signal can come from vibration or from power supply noise, lots of different ways to get noise in a signal. Also, we always use an anti-aliasing filter in a digital acquisition system to make sure we don't have any alias data. So filters are different from other signal conditioning things because they depend on the frequency. So they modify the signal depending on the frequency, not the amplitude or something like that. So they're back into the phasor analysis kind of circuits. And the filter design can be described by a frequency response plot, also called a Bode plot, like we see here. So this is a picture of frequency response of an ideal filter. So we've got amplitude on the y-axis and frequency on the x-axis. And basically, for a low-pass filter, we want to keep low-frequency signals and eliminate high-frequency signals. And the border between low and high is set by the corner frequency or cutoff frequency, Fc. So if the frequency content is below Fc, it's multiplied by 1. If the frequency content has a frequency above Fc, it's multiplied by 0 and eliminated. This is an ideal filter, and we can't do this quite as nicely in practice. Here's an example of using the ideal low-pass filter to filter a signal that's a sum of two sinusoids. So we've got this input 10 cosine 3 times 2 pi times t plus 5 cosine 600 times 2 pi times t. So the 2 pi in here means that this is the frequency in hertz, and that's how our plot is labeled. We've got a 50 hertz cutoff frequency or corner frequency. It's the corner of this graph. It's the cutoff between low and high. So anything below 50 hertz stays, and anything above 50 hertz gets eliminated. And so the output, in general, for a filter response like this, you take the amplitude of the filter at that frequency and you multiply it by the original gain. So our original 3 hertz signal has a gain of, or an amplitude of 10. We see that amplitude down here, and then we multiply it by the output of the function, the filter frequency response, and we keep the sinusoid terms exactly the same, and same thing here for the other term. So this g of f comes from this graph. So in this case, if f is below 50 hertz, g is 1. So on our 3 hertz signal, we've got, it stays, we've got a 1 here. And for our 600 hertz signal, g of f is 0, so we get a 0 in there. So it keeps the low frequency signal and it eliminates the high frequency. That's why it's a low pass filter. So in a system, they come in like this. We've got our sensor, we've got an anti-aliasing or other kind of filter, and then it goes into our data acquisition system. If you remember from phasor math, in circuits class, there's always a phase shift to include with this. So normally we would have a phase shift from our filter. The ideal filter can have 0 phase shift, so that's okay. And the other thing to be careful with is these sinusoids are traditionally in radians per second for their frequency. So whatever is multiplying time is going to be in radians per second. And filters are usually described with corner frequencies in hertz. So make sure you keep track of where that 2 pi should go. Here's what it looks like if we graph the two signals. So the input signal is in blue. It's this with the two sinusoidal terms. So we've got the blue going up and down. So it looks like a noisy or vibrating signal, this high frequency term on top of the low frequency term. I think I changed it to 60 here to make it graph a little bit cleaner from 600. And then the output, we eliminate that high frequency term and we're just left with the low frequency term. So that's the red. So it's smoothed out. So that's what a low-pass filter does. An ideal low-pass filter smooths it out exactly. A practical one will reduce this high-frequency term, but it'll still be in there a little bit. So one nice way to think about low-pass filters is that they're a running average. So if you average this oscillation up and down, it would average out to the red. And so a lot of times when people are doing data acquisition systems, they're building in these running averages to get rid of noise. And really, it's better to design it from a frequency response perspective, because it is the corner frequency is related to how many samples you average together and everything. And it's a little bit more analytical to do it with a low-pass filter rather than trying to keep an average of the last 10 measurements or something. Although if you look at the digital low-pass filter and the running average, the algorithms are very similar to each other. So there are other kinds of filters besides low-pass filters. So this is the frequency response of a low-pass filter. We keep the low frequencies and the high frequencies get eliminated. So this is a practical filter, the kind that you could really make. So it doesn't go straight down to zero. It rolls off, is what we say. So in contrast to that, this is a high-pass filter where it keeps high frequencies and gets rid of low frequencies. And then if you combine these together with different corner frequencies, you can make this one here, which is a band pass. So in a certain band, we keep the signals and we throw out frequencies above the band and below the band. Or a band stop filter that keeps below the band and keeps above the band and tosses the frequency content in a band of frequencies. So here's a practical way to make a low-pass filter. This is called a Butterworth filter. Filters normally named after people. And this uses an extra capacitor on our inverting op-amp circuit to give us that first-order response that we want for a first-order low-pass filter. So the frequency response here is shown. So again, frequency and gain in decibels is traditional. So roughly gain of 1, and then at the corner frequency it gets rolled off. We reduce all the high frequency amplitudes here, and the slope of this line is 6 decibels per octave. So these are both log scales because we have decibels here and a log scale there to make this look like a straight line. You can do this circuit analysis just with straightforward phasor analysis if you replace the single resistor in the inverting op-amp circuit with this capacitor and resistor in parallel, and talk about the impedance. The book goes through this in detail, so it's worth reading that section of chapter 3. It's also worth pointing out that you don't need an op-amp to do a low-pass filter. Just a simple RC circuit will do the job as well. And we'll see that later. So here's a high-pass filter, which gets rid of low frequencies and keeps high frequencies, and still has a corner frequency that is the barrier between, or the transition between low and high frequencies. Be careful with high-pass filters because a constant signal coming into a high-pass here, so if VI is just a constant signal has a frequency of 0 hertz, so it will get completely thrown away, washed out. They call it a washout filter sometimes. And so it only keeps oscillating frequencies. So these are common in things like audio signals where you just want to hear a tone, and other systems where there may be slowly drifting signals that are low frequency that you want to get rid of. If you think of a low-pass filter as a running average, averaging over the last few samples, the high-pass filter is similar to taking the running average and then subtracting that off. So if you have a constant, that's your average, and you subtract it, so the high-pass would be 0 there. High passes are found in nature. Things like getting dizzy is a high-pass filter in your brain, where if you're spinning around on a playground for a while, your brain says, oh, this is normal, I'm just holding still, and then when you get off, it reacts the wrong way because you're stop moving. Your brain actually has a lot of filters, low-pass filters for things like persistence of vision in your eyes, and high-pass filters to wash out some steady-state things, like if your dog gets skunked, the next day you don't notice the smell so bad because that's your nose has a high-pass filter that gets rid of steady-state values of stinky things until your girlfriend comes over and says, "What is that smell?" So anyway, that's the high-pass filter. You can build it with an op-amp, or actually just this RC circuit will do the job too. Okay, so here's an example of using the frequency response plot. In this form where we have an amplitude versus frequency plot right on top of a phase versus frequency plot, that's usually called a Bode plot. It's not Bode, it's Bode. It's named after a person who pronounced their name that way. So these are great. If you see one of these, you don't have to do any calculus. We just use this graph in order to figure out the response. So for this example, we have a sinusoid with 3 terms, each at different frequencies. Here the frequencies are in radians per second, which matches the axis here in radians per second. And we've got an amplitude and a phase of the original signal, amplitude and phase, amplitude and phase. So what we need to do is we need to take the amplitude of the filter, and it multiplies the original amplitudes at the right frequencies. And we have a phase shift for each frequency as well. So for each sinusoid term, you go through and you read this graph, and you figure out what the magnitude and phase of the filter are. So at 200 radians per second, you have to come down here, and this is a log scale, so you have to be a little careful. This is 100, this is 1000, and we go 100, 200, 300, 400, 5, 6, 7, 8, 9, 1000. So each of these lines is increasing, but because it's a log scale, their distribution is different. So we're looking for 200 radians per second. So that's 100, this would be 200. We can find the amplitude is right about 0.3, and the phase is right here. We're calling that 118 degrees. Same thing for 3000. We've got 1000, 2000, 3000. We're up here very close to 1, so 0.99, and the phase at 3000, calling it 15 degrees. And then at 6500 radians per second, we've got 1000, 2, 3, 4, 5, 6, 7. So 6500 is somewhere in here. It's pretty much 1. And we're calling it 5 degrees. So once you make this table of the data from this plot, you just multiply the magnitudes and add the phase. So this is the M of 0.3 at 200 hertz, and the original amplitude of 10, original phase of 10 degrees, and we add our 118. Same thing here at 3000 hertz and at 6500 hertz. So this is a high-pass filter because it's reducing the low frequency and keeping the high frequencies. So this is a really good skill to have, to be able to use these Bode plots or frequency response plots. Alright, so the next video we will look at more filter examples and some basic filter design concepts.